Welcome to a session with time. We are here to discuss some very important concept, aldol condensation, which is part of chemistry. And we have found that there are so many questions in the entrance exams that consider aldol condensation as the base. So we'll take up this aldol condensation, check what this reaction is and what are all the products we get, what is the type of reaction, and so on. So before we begin, let me allow you to note the YouTube channel. Time for IIT JEE NEET. So you will find interesting sessions of this type on various concepts. So this channel would be useful, we hope. Now, this aldol condensation belongs to organic chemistry, to be more specific. And then within this organic chemistry, we have got this chapter, Aldehydes and Ketones, right, wherein we read this aldol condensation. And what is this type of reaction? This type of reaction is a nucleophilic addition reaction. Now, shall we begin getting into the details of this aldol condensation? Now, aldol condensation, what type of reaction is this? What are all the required things for this aldol condensation to happen? Now, aldehydes and ketones, which have an alpha hydrogen, there needs to be an alpha carbon. The hydrogen attached to that is alpha hydrogen. So aldehydes and ketones both give this reaction, but they need this alpha hydrogen atom, right? And this, when treated with dilute solution of alkali, that is when aldehydes and ketones are treated with dilute solution of alkali, we initially get a beta hydroxy aldehyde if you have started with aldehyde, or a beta hydroxy ketone if you had started with a ketone, right? And this particular compound is called aldol. Now this ald means aldehyde or ketone, and this all means a hydroxy compound, alcohol. So when you have a hydroxy and an aldehyde, it becomes an aldol. So when you say aldol, it is actually a combination of either aldehyde or ketone and a hydroxyl group present at the beta carbon, right? Beta carbon means 2 carbons away. The next carbon to the functional group, that is CHO or CO, is the alpha carbon. Next to that is the beta carbon. So we get a beta hydroxy aldehyde or a beta hydroxy ketone, which is commonly called an aldol. Now this aldol may undergo further reaction. What is the further reaction? Dehydration, that is loss of H2O, to give alpha beta unsaturated aldehyde or ketone. So when you start with beta hydroxy aldehyde, this upon dehydration, right, will give you alpha beta unsaturated aldehyde. If you had started with the ketone, we'll get alpha beta unsaturated ketone. Now this is what heating, the aldol needs to be heated. You may also treat with a mineral acid. So you can simply say H+. So even this H+ can do this dehydration. So aldol upon dehydration gives alpha beta unsaturated aldehydes or ketones. I hope this is clear, right? So this is the broad classification of an aldol condensation. Broad details regarding this aldol condensation is this. Now, let us get into some examples. So we have taken here 2 aldehydes. So we have 2 moles of aldehyde, right? And this carbon is the alpha carbon next to the functional group, that is CHO. So we have got alpha carbon on both the molecules. We have 2 moles of that. Between them, when you treat with dilute NaOH, there is formation of this beta hydroxy aldehyde. If you had started with aldehyde, we get a beta hydroxyaldehyde. This is our aldol. But this aldol, upon heating, is going to lose what? H2O to form alpha beta unsaturated. So this is the alpha carbon and this is the beta carbon. Between the alpha and beta, we have got a double bond, right? What has happened in this? In this, there is a loss of hydrogen from alpha carbon and loss of OH from the beta carbon. So minus H from alpha, I'll not put the charge, minus OH from beta. We know that H will go out as H plus and OH will go out as OH minus. But then this is sufficient for us. Minus H from alpha and minus OH from beta. This is what is happening in the heating process, or we said what? Treatment with H plus. That is mineral acid. I hope this is clear. So this is between two aldehydes. So 2 moles of aldehyde. Right? Next, we may take up a case where there is a combination of 2 moles of ketone. So this is a ketone here. So this is what? This is propanone. Propanone is a ketone. So there are 2 moles. 2 moles of ketone. 2 moles of ketone. And what is the base used or alkali? This is barium hydroxide. There we had used NaOH. We could use any alkali which has OH minus. It is actually dilute OH minus. Sometimes you may find that this is only 10%. Means 10% of the OH minus is sufficient for this reaction to happen. Right? Again, what do we get? This is alpha carbon and this is the beta carbon. Right? So alpha and then beta. The beta is having the OH. So this is our aldol. Right? And upon heating or treatment with H plus, you're going to get what? Alpha beta unsaturated. So this is the alpha carbon, this is the beta carbon, and we have got the product. This is acetyl oxide. You start with propanone or acetone, you get acetyl oxide upon aldol condensation. So here we have taken up a case of 2 moles of ketone. Identical. This is identical with this. Both are the same ketones, just 2 moles we have taken. There we had taken 2 moles of aldehyde. Here we have taken 2 moles of ketone. Right? Both have been treated with a dilute OH minus, that is base, right? An alkaline solution, right? Which is a dilute solution. Just about 10% of the base is required, right? So this is the second case we have taken 2 moles of ketone. We may have 2 moles of a cyclic ketone. This is cyclic ketone. Cyclic ketone also has got an alpha carbon, right? So alpha hydrogen is there. In fact, there are 2 hydrogens on each carbon, is it not? So this is also an alpha carbon, right? With 2 hydrogens. Here also we have 2 hydrogens. And then treatment with the base is going to give what? Beta hydroxy ketone. That upon treatment with delta, that is heating, or H plus, right, gives us alpha beta unsaturated ketone. So this is cyclic ketone. 2 moles. So 2 moles of a cyclic ketone we have taken. And there we again get an aldol. This is the aldol here. And aldol will give you alpha beta unsaturated ketone in this case. Clear? So I hope the 3 examples are clear. What we mentioned in the definition of aldol condensation, the same thing we have seen. We have looked at the happenings here. So we've got aldol, and aldol upon treatment with either heat or H plus will give us alpha beta unsaturated aldehyde or ketone, whatever you started with. I hope this is clear. Next, we'll look at the mechanism. So now we have got an opportunity to look at how these things have happened between 2 aldehydes, between 2 ketones, between 2 open chain ketones, and between 2 closed chain ketones. Now, this aldol condensation has been catalyzed by a base. Aldol can also be catalyzed by an acid, which of course we are not going to consider now. So this acid catalyzed aldol we are not looking into now. So base catalyzed aldol condensation occurs through the formation of a carbanion intermediate. So there is a C minus formed. So what does a base do? Base will remove the hydrogen as H plus from the alpha carbon. So this is the alpha carbon, right? The alpha carbon has lost the H plus to the base. The bonded pair of electrons are now on this carbon, so we get a carbanion, right? Why is this carbanion formed at the alpha carbon would be the most important question a student might ask. This is because this minus charge can get delocalized. We know that minus charge or any charge species is unstable. It wants to lose the charge. It wants to decrease the charge. Decreasing the charge can happen only by delocalizing the charge. That is, moving the charge from one atom to the other so that the minus charge is being shared. So each atom doesn't have so much of strain holding the minus charge. So we get a carbanion, right, which is stable. And that is why the alpha carbon is losing the hydrogen, not the beta carbon. Alpha carbon will give a carbanion which is having resonance stabilization. So this is resonance stabilized because of the delocalization, right? So this is why we find that a carbanion in the aldol condensation is a stabilized intermediate. Clear? Now, this carbanion will take up the second molecule. We said that there are two modes or two molecules, right? At the micro level, it is molecule. Collection of molecules is that mole, is it not? So when we read a reaction, we talk in terms of moles because molecules are too small, right? They are not measurable. So we talk about in terms of moles. But then when the actual happening happens, mechanism is at the micro level. So at the micro level, we find that these are molecules. So one carbanion unit is going to attack the other second molecule of aldehyde or ketone, whatever you started with. That minus is going to attack this carbonyl carbon. You know that carbonyl carbon is positive. Therefore, this carbanion will function as a nucleophile, which is why the reaction is a nucleophilic addition. Here, so there is a multiple bond here, pi bond here. So there is an addition reaction. So nucleophile, that is carbanion, is going to hit the carbonyl carbon, which is electrophile, right, coming from the second molecule, right? And then there is a CC bond formed. So this is a carbon and this is a carbon. So this is the new CC bond formed. So new CC bond is formed in the aldol condensation. There is a carbanion as the intermediate, right? And that carbanion intermediate is functioning as a nucleophile. This is going to attack the carbonyl carbon of the second molecule, right? And there is a new CC bond being formed, right? That O minus will pick up the H plus from the water or the surrounding medium to become OH. This is the aldol, beta hydroxy aldehyde. So this is the aldol. Clear? Because we have started with a base, right? We have taken up the base here and we have recovered the base here, right? Means that the base is functioning as a catalyst. Clear? So this is how we get the aldol. That aldol upon heating will give us alpha beta unsaturated aldehyde in this case. Clear? So this is about the mechanism. Clear? Now, we can also show it in this form. This is a more, we should say this is more perfect, right, mechanism. Because the moment the base removes the alpha hydrogen, you get a carbanion. That carbanion will not stay like that. It will delocalize the minus charge onto the oxygen, right? And that oxygen, when it back polarizes, this C will form a bond with that C. So there is a new CC bond being formed, right? And this part of the molecule will remain as an aldehyde. That will become an alcohol. So this is an aldol, ald and the all there. Ald or ketone, right, is together called ald. So ald and the all there will become aldol. So this is an aldol. Beta hydroxy aldehyde in this case. Here. So this is a perfect mechanism, right? See, in the entireness of that, in the entirety of that mechanism, where we also show that the minus charge is being delocalized. So this is the enolate. This is the enolate that we get, right? So if it was OH, it is enol. OH with the H removed is enolate. Here. Next, we had seen so far two identical molecules reacting with each other. It could be two aldehydes or two ketones, two acyclic ketones or two cyclic ketones that we saw. Now we could also have a cross aldol where we may have different aldehydes or ketones interacting. The first molecule may be an aldehyde, the second molecule is a ketone. Or the first molecule is one aldehyde, second molecule is another aldehyde. Or a ketone 1 with a ketone 2, that is called a cross aldol. Sometimes we use the word mixed. Mixed aldol is also used. Some of the books also take mixed aldol as the reaction between two different aldehydes or ketones. Now let us take ethanol and propanol, right, in dilute NaOH. So this is aldehyde number 1, this is aldehyde number 2, right. What we are saying is that we get 4 products out of this. How 4? That we'll see here. Now this is ethanol, right, and this is propanol, correct. Both have got an alpha carbon or an alpha hydrogen. Both can form carbanions. So the carbanion of one may hit the carbonyl of another. So let us say that carbanion 1 hits carbonyl 2, or carbanion 2 hits carbonyl 1, or carbanion 1 hits carbonyl 1 itself, or a carbanion 2 hits carbonyl 2 itself. So we get 4 products, right? Now, how is it that we are going to decide what are the starting materials from looking at the products? We look at the products, we should be able to tell what are all the reactants that reacted to form this. Now, let us take the first case. So, how to identify the reactants involved in the aldol condensation? So, let us take this one. CH3, CH double bond, CHO. I'll show it here. CH3, CH double bond, CH, CHO. This is the alpha carbon, this is the beta carbon. So you're going to get the reactants that form this, right? All that we need to do is break the alpha beta bond completely. No bond between alpha and beta. On the alpha, attach 2 hydrogens to the carbon, to the alpha carbon. And at the beta, attach a double bond O. Now look at this. CH3CHO, ethanol. What is this? This is also CH3CHO, ethanol. So, 2 ethanol molecules have formed this one. So, carbanion 1 hitting carbonyl 1. Now, let us look at the second case. Here itself we'll do. This is the alpha. This is the beta. On alpha, what are we going to do? Put 2 hydrogens. On the beta, you're going to put a double bond O. Now look at this. This is propanol, CH3CH2CHO. This is also propanol, CH3CH2CHO. So carbanion 2 has hit carbonyl 2. Now let us look at the third case. Alpha, beta. Break this. On the alpha, put 2 hydrogens. On the beta, put a double bond O. So this is ethanol, and that is propanol. Yes. So carbanion 1 hitting carbonyl 2, correct? And then look at the fourth case, alpha, beta. On alpha, put 2 hydrogens, so make it CH3. And here you put a double bond O. So this side is propanol and that side is ethanol. That is how we get 4 products. I hope this is clear. So this is between 2 different aldehydes. You could also do between 2 different ketones, or between an aldehyde and a ketone. That is also coming at a cross or mixed aldol. Now, let us test our knowledge by doing this question. So, let us first do this. The compound that is not formed when a mixture of ethanol and propanol is heated. Look at this. This is alpha carbon. This is beta. Break this alpha and beta. On the alpha, put 2 hydrogens. On the beta, put a double bond O. This is propanol. That is also propanol. So this is okay. Next structure. Alpha and beta you break. On the alpha, put 2 hydrogens. On the beta, you put a double bond O. This is ethanol. And that is propanol. CH3CH2CHO. This is also okay. Third one. Break the alpha beta bond. Here you put 2 hydrogens, so this becomes CH3. Put a double bond O. This is CH3CH2CHO, propanol. that is ethanal. This is also okay. Fourth one, this is not alpha beta unsaturated. This is beta gamma, which will not happen. So this is the one that is not formed when ethanol and propanol are heated with dilute NaOH. Though you may get CH3CHO and then CH3CH2CHO, but beta and gamma will not have the unsaturation. The unsaturation is always between alpha and beta. Therefore, the fourth case is not formed. I hope this is clear. Yes, so we have tested our knowledge successfully. Yes. Now cross aldol between acetaldehyde, that is ethanol, and formaldehyde. Formaldehyde has got no alpha hydrogen. So formaldehyde cannot give any carbanion. So we'll form the carbanion here on acetaldehyde and hit the carbonyl carbon of formaldehyde. So we'll make a CH2 with a minus, and that is going to hit the carbonyl carbon of formaldehyde. And then what are we going to get? We'll get, upon treatment with dilute alkali, this is the alpha carbon, this is the beta carbon. So this was the alpha and that is a beta. So beta is having CH2OH, the alpha is having the CH2, and then we have a CHO. So this is our aldol. Yes. That aldol either with H plus, that is mineral acid, or upon heating will form alpha beta unsaturated aldehyde in this case. So this is acrolein. Here. So here we do not have a case where formaldehyde will give a carbanion. Formaldehyde has got no alpha hydrogen. Whereas acetaldehyde, that is ethanol, has got a carbanion. Ethanol can also heat itself. We'll get a product based on ethanol carbanion hitting ethanol carbonyl. That can also be possible. So there are two products here. Here. Next, when you have an aldehyde and a ketone, both having alpha hydrogen, where do you make the carbanion? Carbanion can be made on the ketone or also on the aldehyde. But we know that aldehydes are more reactive for this nucleophilic addition reaction. So we make the carbanion on the ketone and hit the carbonyl of aldehyde. Right? So the product that you get is mostly from this reaction. A C minus from a ketone hitting a CHO of an aldehyde. Here. So aldehyde will provide the carbonyl carbon and ketone will provide the carbanion. Right? This is because the ketone is less reactive towards nucleophilic addition. And we know that aldol condensation is a nucleophilic addition. So the addition has to happen on the aldehyde. So make the carbanion at ketone and then hit the aldehyde carbonyl. Here. So look at this. So make this as CH2 with a minus. Now you know the mechanism. Hit the aldehyde's carbonyl. So we have got a CH3. This has become CHOH. Yes. And this is the alpha carbon. So this is the beta carbon. So this is the aldol. Upon heating or upon treatment with H plus, we get alpha beta unsaturated ketone in this case. I hope this is clear. So whenever there is an aldehyde in ketone, both having alpha hydrogen, make the carbanion on ketone and then attack the aldehyde's carbonyl. But then this is only a major product. Right? We can also get minor product by aldehyde hitting itself. There is carbanion of aldehyde hitting carbonyl of aldehyde, or carbanion of ketone hitting carbonyl of ketone, or carbanion of aldehyde hitting carbonyl of ketone. That is also possible, but less extent, right? To a very less extent, you will get those things happening. I hope this is clear, right? Now, aldol can also lead to cyclization. How? Through an intramolecular reaction, intramolecular aldol condensation. Now, let us look at this 6-oxoheptanal. Now, we said that carbonyl of aldehyde has to be hit by the carbanion of ketone. So, this is a ketone here. So, there is an alpha carbon here. There is also an alpha carbon there. If this alpha carbon hits this carbonyl, we get a 7-membered ring. Right? You can number the carbons here. CH3 carbon is 1, 2, 3, 4, 5, 6 and then 7. The carbonyl aldehyde is 7th carbon. So you get a 7-membered ring. 7-membered ring is not very stable. In fact, formation itself is difficult. So a 6-membered or a 5-membered, that is what we wrote here. A 5-membered or a 6-membered ring will be formed easily, right? So we make a carbanion here and then hit this carbon of aldehyde, and then we get a closed ring, 5-membered ring, and then upon loss of H2O, there is loss of H2O because we need to heat. Heating is required here. That has not been shown. So you get an alpha beta unsaturated ketone in this case here. So this is the aldol condensation leading to cyclization. So there is a cyclization happening, right? So this is an intramolecular or internal aldol condensation. So aldol condensations can be of various types, right? You could take 2 aldehydes, 2 ketones, whether cyclic or acyclic, or an internal aldol condensation to form a cyclic product, right? Which is still alpha beta unsaturated carbonyl compound. Now, very closely related to this aldol condensation is the Claisen-Schmidt condensation. Now, what is happening here? You would take an aliphatic aldehyde or an aliphatic ketone, both containing alpha hydrogen, and then hitting an aromatic carbonyl aldehyde, right? So this aromatic aldehyde has got no alpha hydrogen. Alpha hydrogen is present in aliphatic aldehyde or aliphatic ketone. So they will provide what? They will provide the C minus. And what does the aromatic aldehyde provide? It provides a C double bond O. So it provides a carbonyl group. So this C minus is going to hit the carbonyl carbon. So that is also an aldol type of thing. But here you have specifically mentioned that it's an aromatic aldehyde. Here, same dilute alkali, same alpha beta unsaturated compound at the end of this reaction. Right? Look at this. Now there is no alpha carbon on the benzaldehyde, aromatic aldehyde. So make a CH2 with a minus, since you know the mechanism. Hit this carbonyl carbon, and the same C6H5 will now become C6H5 CHOH, CH2 CHO. So this is the alpha carbon, that is a beta carbon. So this is the aldol, and that can undergo loss of H2O, right? Loss of H2O upon heating or upon treatment with a mineral acid to form alpha beta unsaturated aldehyde in this case. So this is cinnamaldehyde that we get, right? So this is Claisen-Schmidt condensation. One very important application of this we'll find here when you treat that with a ketone. So we said it could be aldehyde or a ketone. We have now showed with an aldehyde, right? We'll now see with a ketone. Now in this ketone we have got 2 alpha hydrogens here and there. So make this a CH2 minus, hit this, make an OH, you got that. So this is alpha carbon, that is beta carbon, and then lose H2O upon treatment with heat or treatment with mineral acid, and then get the alpha beta unsaturated ketone. But then this alpha hydrogen is still there. So we can have one more benzaldehyde molecule reacting. Yes, as you find it here. Yes, so there is one more benzaldehyde. Again, make this CH2 with a minus. This CH3 is here. That is going to hit this, and you are going to get again the beta hydroxy from the second molecule. And then upon loss of H2O, we get an alpha beta unsaturation here. We also have an alpha beta unsaturation there. So this is cinnamon. Then dibenzyl acetone. So this is a special case, and there has been, I have found in the recent times, 2 questions based on this. Now let us look at this. Now let us have a general look at this structure. How many pi bonds are there? Because the next question that is going to come up is finding out number of pi bonds. So 1, 2, 3, 4, this is 5, this is 6, 7, 8, and then 9. So cinnamon has got 9 pi bonds that is being asked in this. So 2 moles of benzaldehyde and 1 mole of acetone, that is what we got there. So we got this cinnamon, right? CH, double bond CH, single bond C double bond O, CH, double bond CH, then the benzene ring. So in the benzene ring we need to show that combination of 3 pi bonds. So 3 here, 1 here, 1 here, 1 there, and then 3 there. Put together is 9. So there are 9 pi bonds in this product. I hope this is clear. Yes. There is one more question I said, which has come out in the recent times, right? In the JEE main. Now in the Claisen-Schmidt reaction, to prepare 351 grams of this dibenzyl acetone using 87 grams of acetone, the amount of benzaldehyde required is. What is the reaction? We said how many moles of benzaldehyde are required? 2 moles of benzaldehyde required for every 1 mole of acetone. So that will put it up here. So I'll write here 2C6H5CHO plus CH3COCH3, that is acetone, is giving us what? Once again, dibenzyl acetone. So benzene ring, CH double bond CH, single bond C double bond O, then CH double bond CH, and then the benzene ring. So this is what we found. So how many grams of acetone we had taken? 87 grams. Now when you write a reaction is written in terms of moles. We read in terms of moles, not in terms of grams. So get this 87 in terms of grams. So whatever weight is there divided by the molecular weight. Molecular weight of acetone is 58. This is the number of moles of acetone. And what is the grams of dibenzyl acetone? 351. And then you'll have to divide it with the molar mass. Each phenyl is 77. So 77 and a 77. There are how many carbons in between? 1, 2, 3, 4 and 5. So 5 12s are 60. How many hydrogens? 4 are there. How many oxygens? There is 1. So 60. Add up. 7 plus 7, 14 plus 6 is 20 plus 4 is 24. This is 14 plus 2 is 16. 16 plus 6 is 22, 23. So this is 234. So 351 by 234. If you do the calculation, this is 1.5. That is also 1.5. For every 1 mole of acetone, you require 2 moles of benzaldehyde. So number of moles of benzaldehyde will be how much? Number of moles of C6H5CHO required for this reaction is twice 1.5, which is 3 moles. All that we need to do is get the grams of benzaldehyde. That's it. Each benzaldehyde is how much? So 3 into, this is 77 plus 1 carbon, 1 hydrogen, 1 oxygen. Add up. 77 plus 13 is 90. 90 plus 16 is 106. 106 into 3 is 318 grams is the answer. Clear? So Claisen-Schmidt reaction, if you have known this reaction, we know that there are 2 moles of benzaldehyde required for 1 mole of acetone, right? Sometimes you may get a question based on excess and limiting reactant also. But in this case, both the moles are same. This and this are same, right? Of course, what is being asked is the grams of benzaldehyde that is required. So this is not to be considered now. Now, this compound is to be made. Now you know that this is alpha, beta unsaturated compound. So you want to find out, you want to make X, right? There is a student here, Aman, right, who wanted to synthesize this molecule X. He thought of this aldol condensation because we know, as we have seen here, there is an alpha beta unsaturation. So he thought that he could do some aldol condensation and get this, right? To get this aldol condensation done, we need dicarbonyl compound, right? So he found cyclic alkenes in his lab, and then he wanted to perform some ozonolysis reaction, reductive ozonolysis, right, which will give us a dicarbonyl compound, followed by aldol reaction to prepare X. Now you have to predict the suitable alkene that can lead to the formation of this. So shall we put the structure in the next slide, right, slightly bigger. It's a 5-membered ring, right, and there is a double bond there, and there is a C double bond O and a CH3. This is alpha carbon, there is a beta carbon. On the beta carbon, there is a hydrogen which you have not shown. Now we are showing. How to get the starting material out of this? We have mentioned that you break the alpha beta bond completely. On the beta, attach a double bond O. On the alpha, attach two hydrogens. So what do you get? This is, you take this as carbon number 1. 1, 2, 3, 4, 5, 6, and then 7. So I'll put here 1, 2, 3, 4, 5, 6, 7. The first carbon is the aldehyde, that is CHO. Then we have a CH2, 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 all these things. At the sixth carbon, there is a double bond O, and then we have a CH3. This is the, is this the starting material? This we need, this we have to get as a starting material, because this upon aldol would give that. What will form this? The alkene upon ozonolysis, O3 with a Zn water combination. That should give us this. In ozonolysis, what happens? Whatever carbonyl carbon you get, those carbonyl carbons you need to join with the double bond. That's it. So if this is carbon 1, this is 2, this is 3, 4, 5, 6, and then 7, right? So we make a 6-membered ring first. And if this is carbon number 1, this is 2, 3, 4, 5, 6, right? On the 6th carbon, there is a CH3, right? 6th carbon has got a CH3. Between the first carbon and the 6th carbon, you need to have a double bond. So this is our starting alkene, right? Which upon ozonolysis gives this. This is O3, ZnH2O. That upon aldol would give us this, which is compound X. So to form X, you start with this cyclic alkene. How do you name this? Methyl cyclohexene, right? So using this, we are able to get the product which the student wanted to make. I hope this is clear. Yes. Now, there are 4 compounds given. We have to find out which will undergo dehydration most readily. Now you know that in aldol, so you have to take the hint from aldol. Aldol will dehydrate easily upon heating or upon treatment with acid, that we have seen. So what is aldol? Beta hydroxy aldehyde or ketone. Now let us check. This is alpha, this is beta, this is gamma hydroxy. This is alpha hydroxy. This is alpha, this is beta hydroxy. So this should be easily done. This is alpha, beta, this is gamma hydroxy, right? So you got the hint. So undergoing dehydration is easy for an aldol, right? So this is the third compound which will easily undergo dehydration to form alpha beta unsaturated ketone in this case, because you have started with a ketone. Here. Now there is one more question, right? As something to do. The product B in the above reaction is, I'll only give a hint here. This is propyne, this is acid catalyzed hydration, and we get C double bond O, C. So this is acetone. All that we need to do is that acetone should be subjected to what? Aldol condensation, and we get acetyl oxide, right? It's so clear. So I am not giving any answers here, right? You can select for yourself. You can break the alpha beta bond, right? That can be done, and then get the starting material, that is acetone. Here. So I hope this session was sufficiently useful. So we had seen different aspects of this aldol condensation and how questions can come in the entrance exams, right? Not only JEE Main, even for NEET or CUET or any state entrance or even BITSAT for that matter, right, can have questions based on aldol condensation, because we have seen that we can make many questions from aldol condensation, and which is why many entrance exams carry this aldol concept, right, for making questions. I hope you would have done well, understanding the session, right? And many more such sessions you will find in our YouTube, right? So see to it that you get in touch with us, right, for any type of exam that you need, JEE, NEET or CUET or BITSAT or any other related exam, right? So I hope the session was useful. And if you want any classroom coaching or you want online courses, you can get in touch with us. All the details are given here, right? And for the remaining part, right, our best wishes. Thank you. You can get in touch with us and then make us as part and parcel of your successful journey. Thank you.